Hello, year 13. So it's Tuesday. I'm actually recording this on Sunday, Tuesday, period 5. You might be accessing it any time of the day, of course. Very sorry, of course, that we're not in school. I'm recording this on Sunday, and I have a meeting tomorrow morning to discuss things going forward. So you may well have heard from me by now as to some further detail as to things like trial exams. But for the meantime, as of course we do need to get on with the course, my plan will certainly be to be just continuing with the course at this point, and then the trial exams will come in when they come in. So I've got a couple of starter questions here which I've popped onto the classroom as a PDF. You can do them on the sheet printed out, or you can do it in your book. You will need to be evidencing your work as we did during the first lockdown, please, thoroughly, and uploading it as a single PDF. So have a go at this, pause it here. I'm going to do it just as soon as you've done that. Ooh, just with space. Okay, so just a standard complex numbers question, because of course we are doing, this is FP1 as in the old FP1, not the current FP1. We know that if we have complex solution, then the complex conjugate is also a solution, so that's the third root. And we can find the original cubic by considering the quadratic factor. So let's do the reverse process of completing the square here. That's a minus 25, of course. If you expand those brackets, add the 25. Okay, and then therefore we've got the factor of 2, sorry, the solution of 2, so the factor of x minus 2, and also the quadratic factor. And that is equal to the original cubic, x cubed plus px squared plus 30x plus q. Right, so I can find q by doing minus 2 times 26. So q must be minus 52. And if I compare the quadratic terms, I've got minus 2x squared, and I've also got minus 2x squared. And that's equal to px squared. And so p must be equal to minus 4. And then part C, on an argand diagram, I've got the solution of 2, x is 2, y is 0, and I've also got 1 plus or minus 5i, so I've got 1 minus 5 and 1, 5 there. Good, right, that's question number 1. Question number 2, I've got a proof by induction question. I'm actually going to just create some space to do this on 2 separate pages because I know I won't fit them both on. Right, so this is from the old FP2, proof by induction. That's now, of course, in the CP modules. Right, so the standard process, let's start with n equals 1. So 2 to the power of 5 plus 5 to the power of 2 equals 32 plus 25. Which is 57, and yes, that does divide by 3 because it's 19 times 3. And then we're going to assume true for n equals k, and therefore f of k, which is 2 to the 3k plus 2 plus 5 to the power of k plus 1. We're going to assume that divisible by 3. And then let's go for n equals k plus 1. So 2 to the power of, that will be 3k plus 3 plus 2. So 2 to the power of 3k plus 5 plus 5 to the power of k plus 1 plus 1 will be 5 to the power of k plus 2. So if we try and get some of the original back in there, if I factor, I want that power to drop from 5 to 2. So if I factor out the 2 cubed, that will leave me with 2 to the power of 3k plus 2. And if I factor out a 5, that will leave me with 5 to the power of k plus 1. So obviously that's 8 and that's 5. So if I factorise out the smaller of the two, I mean, you could do the bigger and then it doesn't matter really. So 5 lots of 2 to the power of 3k plus 2 plus 5 to the power of k plus 1 plus an additional, that's 8, so I need 3 more of those. So what I've actually got there is I've got 5 lots of f of k plus 3 lots of 2 to the power of 3k plus 2. And that is sufficient because f of k is a multiple of 3, divisible by 3. And this is obviously divisible by 3 as well because we factored out a 3. So therefore, shown that if true for n equals k, then true for n equals k plus 1, as true for n equals 1, true for all positive integers. Okay. Okay, and the third one, let me just tidy this up a little bit. No, I can't do that. Let's move over there. So I've got a matrix one here. So let's do the same process, n equals 1. So the left-hand side is just -2, 9, -1, 4. The right-hand side is 1, -3, -1, 9, and 3 plus 1, which is -2, -1, 9, and 4. So therefore it's the same. Good. Assume true for n equals k. So we're going to say that -2, 9, -1, 4 to the power of k. Now, some of these steps are a bit laborious. Obviously, this one is laborious, which is copying. But I do find that when you take the time to follow the structure, follow the process, write the steps out, actually helps you to answer the question because you get time to be thinking about it and really take it in as you're writing it down. So I do find it's not pointless. Right, n equals k plus 1. So clearly we've got -2, 9, -1, 4 to the power of k plus 1. And that is equal to -2, -1, 9, 4 to the power of k, and then another -2, -1, 9, and 4, like so, because that's a power of 1, isn't it? Now, we know that that one there, the power of k1, using this down here, is 1 minus 3k, 9k, minus k, and 3k plus 1 times -2, -1, 9, and 4. And we're going to times those, and we're going to make sure we are doing a proof here. So we're going to show what we're doing. We're not going to just write the answer down because then we'll be arriving at the answer too quickly. So we've got 1 minus 3, we've got that one times that one, and then that one times that one. So we've got -2 plus 6k, okay, minus 9k, that's okay, minus 9k there. On this next one down, I'm going to start simplifying those. So I've got -2 minus 3k, okay. And then I've got over here, I've got -1 plus 3k minus 4k. Okay, so if I simplify that, ready for the next step, that'd be -1 minus k. And then I've got minus 18k, and then that would be plus 27k plus 9, which is 9k plus 9. And I've got this one here, which is minus 3. Oh, sorry, that's the wrong base. Minus 3 minus k. That's not right, sorry. Minus 3k minus 1. Minus 3k minus 1. Oh, that's not right either. Sorry, I've got myself confused there by moving between these two things. Sorry, I just did I did that one and that one. Now I'm doing that one and that one, sorry. Minus 9k plus 12k plus 4, which is 3k plus 4. So hopefully I've not made any mistakes on this. We'll find out. Hopefully that's the same as 1 minus 3 lots of k plus 1. Let's check that. Minus 3k at minus 3 plus 1. That's correct. That's the same as 9 lots of k plus 1. Yes, it is. Minus 1 minus k is the same as minus brackets k plus 1, of course. And that's the same as 3 lots of k plus 1 plus 1. And that's exactly what I want. So I've shown that this is true. So therefore, I've got the same conclusion. It's good to keep writing it down. Showing that if true for n equals k, then true for n equals k plus 1. As true for n equals 1, it must be true for all positive integers. Good. Right. So this is what I set on the last lesson before Christmas. Obviously, we're not currently doing the trial exams. You've heard all the same government announcements that we've heard, and you might have heard from me in the meantime. But keep going with your paper revision. We need to keep everything fresh, so that is useful for you, of course. I'm going to now continue to move on. So you can see the notes which are there on the classroom. We're going to start off by proving de Moivre's theorem. But have a look at the theorem here and just take a minute to understand what that theorem is actually telling you. What this theorem is telling you is that when you raise any complex number in modulus argument form to a power, it's telling you that you can apply that power directly to the modulus, which you would expect because it's a bracketed term. But more interestingly, it's telling you that you can apply it to the argument as a multiplier. This means that you can, as long as you've got your complex number in modulus argument form, or of course exponential form, you can simply apply any power really quickly and easily without resorting to a long binomial expansion. And this is really useful, and it's got various applications in expansions and integration, as we will see as we move through this topic. So it's very useful. But the first thing I'm going to do is I'm going to just prove this. So you can follow through on the notes. You can see the gaps on the notes. I'm going to prove it for positive integers. You can see the proof for negative integers as well in the textbook, and you can also extend it fairly straightforwardly using exponential form, as I'm sure Kingston will point out at the first opportunity. So let's start with n equals 1. So the left-hand side will simply be the simple term there, and the right-hand side will be r to the power of 1 cos 1 theta. I'm just going to write it as exactly as I can. Sine 1 theta. Okay, so they're the same. Good, right. Assume true for n equals k. Dum, dum, dum. So I've got r, bracket there, cos theta plus I sine theta to the power of k. That will be r power of k, and then this is this one's a multiplier, which is really the key bit of the theorem. Okay, let's try n equals k plus 1. Okay, so if you've got a power of k plus 1, you've got a power of k, haven't you? You've got the k, and then you've got, not equal, sorry, then you've got another one. Okay, so clearly then, using the line above, that will be rk cos k theta plus I sin k theta. Okay, you're going to times those r terms, which will give you the rk plus 1, and then we're going to start timesing these as we've got cos k theta plus I sine theta cos k theta plus I sine k theta cos theta plus, oh no, it's not plus, it's I squared, so it's minus sine k theta sine theta. Okay, and that is r k plus 1. Let's group some terms. We've got cos k theta minus sine k theta sine theta plus I, and let's factorize the I out there, sine theta cos k theta plus cos theta sine k theta. Okay, and then let's come over here. Whoops, didn't mean to cross that out. rk plus 1, and then that is cos k theta plus theta. Remember, the compound angle for cosine's got the opposite sign, and the other one is sine k theta plus theta, which could also be written, factorised out of theta, as k with a k plus 1, like so. Therefore, oh my goodness, I'm going to test my patience by writing it for a third time. Just need some tea to prepare me for writing it for a third time. Therefore, shown that if, that's the key word there, if true for n equals k, then true for n equals k plus 1. This if is really important. As true for n equals 1, true for all positive integers. Right, good. So that's the theorem. It's very useful. We're going to apply it in some fairly basic situations in this first lesson today, and then we'll extend it over the next week or so. So we're raising this to the power of 7. It's already in modulus argument form. So this simply means, bear in mind there's a 1 on the outside of this. Let me just go back and make that really clear. There is, if we put a bracket there, there is a 1 there. So you would start by doing 1 to the power of 7, which in this case has no effect. And then you've got the 7 pi on 3 running through there. But you don't want to have an argument which is not between minus pi on pi, or certainly between 0 and 2 pi. 7 pi on 3 is too big. So what we're going to do, the 1 to the power of 7 in this case isn't doing anything. We're going to unwind that complex number by removing a 2 pi, and that will just take you back down to pi on 3. Always unwind your complex numbers, because every time you go another 2 pi, you're just going round in a circle and it doesn't achieve anything. This one, of course, is not currently in the right form. So we know we've got a 1 on the outside. We've seen how we can adjust them to get them in the right form. That's now a plus. So this is the adjustment that we've seen many a time. Yeah, and then that's all to the power of 10. And so that will give me 1 to the power of 10, which of course is just 1. And then it will give me cos, timesing that through, because the power becomes a multiplier. Now this is not between minus pi on pi. So I'm going to add 22 pi on 11 to those arguments, which is just 2 pi, isn't it? And then the 1 doesn't do anything, so I've got cos 2 pi on 11. There we go, which is the answer. Next one. Nearly there. Right, so I've got a division, and I've got something that's not in the right form. So let's sort this out. On the top, I can go straight there. Again, I've got 1s on the front. It's not going to make any difference. I can go straight for cos 5 pi on 4 plus I sine 5 pi on 4. And on the denominator, of course, I'm needing to change that to cos minus 3 pi on 5 plus I sine minus 3 pi on 5 to the power of 8. So I can't apply the power until I've made that change. So then I've got cos 5 pi on 4 plus I sine 5. It's not working very well, this tablet today. Sorry about that. Also, my writing is not very good. So that becomes cos minus 24 pi on 5. Like that. And then finally, I can then apply the rule for division of complex numbers. And remember, the rule for division of complex numbers, let me just write it really clearly here. R1 cos theta 1 plus I sine theta 1. We covered this ages ago in CP2. Sorry, CP1, beginning of CP1. There's the rule. So if we're dividing complex numbers, we have modulus divided by modulus, but we have arguments subtract argument, don't we? So remember that rule, because you do need to use that rule with confidence. That's the rule for dividing complex numbers. So my modulus is just 1 and 1, so therefore it'd be 1. And when I subtract those, it's a double negative, of course, I get cos 121 over 20 pi. So you might be using your calculator to do that. That's supposed to just be a closed bracket. 121 over 20 pi. This is obviously way too big for an argument. I'm going to subtract multiples of 2 pi, which is 40 over 20. And actually, in this case, I can unwind that complex number 3 times, which is 120 on 20 pi, to leave me with just the pi on 20 there, which is the answer. Right, last one. Final. So we've got a complex number here written in a different form. So I'm going to write it in modulus argument form. 1 plus root 3 is up there. Okay, so there's my complex number. I'm going to find my modulus by doing 1 squared plus root 3 squared, which is root 4, which is 2. I'm going to find my arguments. So it's complex over real, and I know from my table of values that will be pi on 3. So, of course, you could be using, very easy to just use let me do this in two. I want to do this in two ways. So I want to use the exponential form as well, because I've not really mentioned that. So in exponential form, my complex number, let's call it z, my complex number is 2e to the pi on 3I. And so that means that z to the power of 7 is, if you apply those powers, pi on 3I to the power of 7, we know the rule is to multiply powers with brackets. So I've got 128e to the 7 pi on 3I. And you can do the same thing here with the argument 7 pi on 3, unwind that by a 2 pi, and that will give you e to the pi on 3I. And then, of course, you can go back to modulus argument form, which will be cos pi on 3 plus I sine pi on 3. And then from modulus argument form, that's a 7. From modulus argument form, you can, cos pi on 3 is, of course, a half, and a half times 128 is 64. And sine pi on 3 is, of course, root 3 over 2, which will give you 64 root 3I, clearly outside the square root. You can follow the same process if we've got modulus argument form. So we've got 2 cos pi on 3 plus I sine pi on 3 to the power of 7. And so we end up with 2 to the power of 7, which is 128. Cos 7 pi on 3 plus I sine 7 pi on 3, and then we can reduce that down to the cos pi on 3 plus I sine pi on 3, and then of course we're already at this stage and we end up with the same answer. So either way, we've got our complex numbers in x plus I, y, we've got them in exponential form, and we've got them in modulus argument form. These forms, i.e. modulus argument exponential, are much more useful because we can apply de Moivre's theorem straight away than x plus iy, although x plus iy is quite useful for plotting on an argand diagram. Good, right, so there is some questions to do for that. There's quite a few questions there. I will set the deadline on the classroom, and after the deadline, I will go through and check that that's done. So please ensure that you're uploading the work as PDFs by the deadline, because I will be going back to the process I did during the lockdown, where I'll be checking that work thoroughly as soon as the deadline has passed. Okay, thanks very much. Let's close that.